1.3 topic question number 6. I'm not going to jump into immediately trying to solve this because this problem brings into or could benefit from a review of some of the salient points about free fall. When we drop something, okay, when you think free fall, until further notice, free fall just means my acceleration is constant and it's downward. The force that does this, a common force that does this, is gravity. So we often use little g to represent a downward acceleration due to gravity. Free fall is pretty straightforward when you're just dropping stuff because you're going down and the acceleration is downward and it's just this. So it's literally, it's like saying, hey, if a car starts from rest and it accelerates to the right, it's going to gain some final velocity, right? And v naught equals 0. If I accelerate over some time t, I get a velocity this way. You get graphs like, your velocity time graph could be I start at rest, I'm accelerating at a constant velocity, so it's linear, and the slope of that line is a. Okay, when you're dropping things, if downward velocity, if I take this picture and I tilt it, or I rotate it this way, right, downward is positive. In this case, to the right was positive, but I rotate the whole picture this way, I get downwards positive, and you get the idea. I've got a velocity increasing downward at as constant acceleration, and if it's free fall, yeah, it's g, right? That acceleration is g. It gets a little it gets a little trickier, or there's some factoids that pop out when you've got a downward acceleration acting on something that's moving either up or down. But like for this problem, it's thrown upward. So that one's a little bit different because that, if we look at a horizontal example, you get something like this. Same idea. I've got A, but now I've got an initial velocity that's not 0. And if I throw it up, right, g is always downward. So if we take this idea and just customize it to free fall, meaning vertical motion, really, not just falling, but my object is moving up or down with a constant downward g. A simple problem number 6 is like the basic system. What's the basic system? I have a velocity, I might have an initial velocity that's upward. And it's thrown up. So as soon as it's accelerating downward at g, that means nothing else is touching it. Okay, so it's just going straight up. So my acceleration is opposite my velocity. That means at some point, my final velocity at the top, my final velocity is going to be 0. Then I start my downward journey. So now I've got an initial velocity of 0. And I'm going to accelerate downward at g until I hit some velocity. So the factoids you can count on, and if these factoids don't make sense to you, if you're like, I don't understand why, then let me know. But hopefully that you're okay with the factoids as follows. I must have done this over some distance, right? So let's say it's a certain height from here to here. If you look at the kinematics equations, right, especially the timeless one, you can see that for the same h, I've got a g. If I have an initial velocity and a final velocity of 0, that v squared equation, right, all these conditions have to satisfy this. And if we look at free fall, what's happening? I've got my final velocity of 0, I have an initial velocity v naught squared, but I've got a negative g, and I'm going h. If we look at what happens when I drop the thing, I've got, using the same equation, what happens now? I have a v squared downward, but so that's a negative. It's going to be a negative number, right? But I square it, becomes positive. The result's positive. My v naught squared is 0, and I'm still accelerating downward, so I have 2g, and I'm falling through the same distance, right? H. So what does this mean? Hopefully you could see that this means that my initial velocity's got to equal my final velocity. And I can only say the magnitude. It's got to be the magnitude, right? Because to mathematically do this, you end up taking a square root, plus or minus, blah, blah, blah. But we know the magnitude of the two is the same. Okay? The directions have to be different because this is upward, this is downward. So there's the actual velocity vectors are, one's up, the other's down. But the magnitude is the same. So that's one thing. In Freefall, where there is a return journey, up, then down, this is true. Right? So I end up, by the time I end up where I left, right, at the same level, my velocities, my speeds are the same. Not velocities, because one's up, one's down. Okay? The other factoid you could take is the following. If it takes t seconds, if I play this movie and I see the ball go up, stop, and then fall back down, if that takes t seconds, then the other factoid is if t is the whole journey, is time for up and down, then the time to go up, my up time, is equal to my down time, and that's going to be half of that. So there's a symmetry, right? If you just look at my up and down motion, I'm in the absence of air resistance, which we'll get to later. In the absence of air resistance, the amount of time it takes me to go up should be the amount of time it takes me to go down because of these identical conditions. Okay. All right, so let's tackle number 6 now. Oh, one more thing. What does this whole journey look like in terms of that time? Simple sketch, really. Again, if velocity, if up is positive, then you're going to start at some initial velocity, v naught, right? Because I'm going to get thrown up, right? I'm not throwing up, but if an object is moving upward, then the moment that my downward acceleration is only g, is actually g, means only gravity is acting on me, then that means I've let go of the ball because I'm not pushing it up anymore. Only gravity is pulling it down, but I've achieved some initial velocity. My graph is going to look like this, right? What's that slope? That slope is minus g. And the amount of time it takes, this time point right here should be half of the total time interval. So there's your half t, and this is your total time in the air. Okay? All right. So let's bring all that to bear on number 6. In number 6, we have that they want to know how fast something's going at 2/3 TF, and it's in terms of G and TF. Okay? So there's more than one way to do this. In fact, there's more than one way. There's at least 2 ways probably to do every single problem we've been talking about. So let's tackle this one. I'm going to clean up the board, so I'll put the actual solution in another video.